Today I will discuss about the error analysis. So, when we do experiment, so that whatever the precision of the measurement, so we cannot tell that our data is error free. There will be error. So, only what we can do, we can try to find out the best value of our parameter, which we want to find out from the measurement. Okay. So, that what is error? Basically, if we ask this question, what is error? So, this error generally we define the error as or by the difference between an observed or calculated value and the true value. So, some standard values are available, and for the same parameter we have done experiment and find out this that parameter, and then whatever the parameter experimentally we got the value of the parameter, that we compare with the standard value, that is we are telling true value, and see this how close our value to the true value. So, the difference between this true value and our experimental value, so that we take as a error in our measurement. Okay. But problem is, usually in most of the cases we do not know the true value or standard value, otherwise we would not need to perform this experiment. Okay. So, most of the time what happens, generally we may know approximately what it should be. However, either from some earlier experiments or from some theoretical predictions. Okay. So, that value is not true value, it is the available experimental value or the theoretical value. Now, we are performing experiment to find out that parameter, and then we check whether our this measurement value, how close it is with the earlier experimental value or the theoretical value. Okay. So, that way we check our data, we check our result with standard or true value or some available values from theory or other experiment. So, such these approximations can serve as a guide, but we must always determine in a systematic way from the data and experimental conditions how much confidence we can have in our experimental result. Okay. So, we will do experiment and find out the result, and that result we will compare with the true value or the available experimental value or the value predicted by the theory, and then basically we will have confidence in our measurement, in our results. So, this is the way we generally get confidence on our measurement and measurements and our result, and that is basically we are estimating the error in our measurement. So, how to estimate the error in our measurement? and what are the sources of error and how we can minimize error. So, that is what we will discuss. We will discuss also what precaution we should take to minimize the error. So, that is the aim for our this lecture. So, so there are some common things, this we should know this. So, when we measure some parameter, say x parameter we are measuring. So, measured value of x, measured value of x, okay. So, that how we will express this measured value of x, generally we express in this way. So, we can generally we write x best plus minus delta x, that means this x best, that is the value we are reporting for parameter x with some error. So, that we have written as a delta x. Okay. So, so this delta x is generally we tell this is a basically absolute error, absolute is the absolute error, absolute error or uncertainties. So, there is another definition of error, this is called relative error. So, that we express by delta x by x. So, this mod x is all the time it should be positive value. So, this we tell is a relative error. Okay. Okay. So, in this class basically we will discuss how to find out this x best and how to find out this delta x, right. And then also how to write, see when we calculate this this parameter, okay, this measured value of x, it may not be just we have measured this value directly. It may happen that this x is related with some other 3-4 parameters which we are measuring directly, and then this x is related with those parameters, and from there basically we are calculating this x. Now, when you are calculating this, you may get after decimal few digit, okay. But how to write that x based means what should be the up to which decimal point we should keep, or so what is the significance of this of the number of decimal number of digits after the decimal points. So, these things we should understand, and we will discuss about it. So, so basically when you are writing this result x best, so we should have knowledge of significant figure, significant figure. Okay. So, what is significant figure, that I have already discussed, but again I will repeat it with some example. So, say it is that significant digit here, it is basically in this case it is controlled by this also, it is controlled or it is related with this delta x, it is related with this error. Okay. So, there should be matching between this x based and this delta x, matching in the sense this after decimal point how many digits should be there, that will be decided seeing the seeing this delta x. Okay. So, let me give you example. So, say you have calculated some parameter, that x, parameter x, that value you got from calculation. So, 6051.78, that is what you got. Okay. Now, x based basically x based. So, how to write this x based? That will depend on this delta x. Okay. So, if delta x is say 0.03. Okay. So, we will discuss later on how we decided this delta x equal to 0.03, that we will discuss later on. Okay. So, that is the main part of this subject, error analysis. So, if this uncertainty error, absolute error is 0.03 and you have calculated your measured value of x, you have calculated 6051.78. Now, how to write this x based plus minus delta x? So, both value x and delta x is available. Now, we have to write our result, final result in terms of x based plus minus delta x. So, x based in this case, if it is, you see here after decimal, this is 2 digits are there. Okay. So, we can claim our accuracy up to 2 digit after decimal. Okay. So, in x based value we can keep up to 2 digit, we cannot keep more than 2 digit. If it is more than 2 digit, that means we are claiming more accuracy. So, we cannot claim more accuracy because our error is telling okay, our accuracy is up to 2 decimal point. Okay. So, this I will write result 0.51.780. This if I put 0, this value is same, but I cannot put 0 third digit, then I am claiming the accuracy up to third digit. So, because this if I put the 0 here, so this 0 is significant digit. Okay. So, that is I have told already, but again I will tell about this significant digit or figure. So, this I have to keep up to second decimal. So, I cannot write 1 0 more here, although these both values are magnitude are same, but I cannot write because it will have different significant. Okay. So, that is what is a significant figure. Okay. So, up to 2 decimal point we can keep. Now, if in your measurement this error, absolute error is say 0.3, then you can show uncertainty or error already in first decimal point. Okay. So, here also x based, then in that case x based you have to write 6051 point now 7. So, now 7 is followed by 8. Okay. So, you can write this 8. Okay. So, this as you know the rules as and I told you also, if greater than 5 or less than 5 or equal to 5, what happens? Again probably I will just repeat it. So, this will be the your x best. So, this way it is controlled. If delta x equal to 3, then you see this accuracy now after decimal point there is no accuracy. You cannot claim the accuracy up to decimal point. So, in this case x best you have to keep 6051. Okay. So, your result basically x you have to write x 6051 plus minus 3. Okay. So, this is the way one has to write the result x equal to x best plus minus del. So, del x. So, this way one has to write their result. Okay. So, next as I told, this significant figure, to find out the significant figure, there is some rules that I will just remind you. So, this what are the rules here, just I have noted down. So, significant figure, the number of digits about the correctness of which we are sure plus the next doubtful digit are called the significant digit. So, what is doubtful digit, that I have discussed, right. So, you can keep the number of digits up to which you are sure about the correctness, as well as you keep one additional digit thereafter which is doubtful, and they generally doubtful, that digit we put in a bracket. Okay. Up to this you can claim as a significant figures. So, if you do not write the doubtful digit, that is also fine, but if you write, then maximum one doubtful digit you can write. Okay. So, either without doubtful digit or with doubtful one digit. So, that we tell this significant figure. Now, rules for finding significant figures is that this all non-zero digits are significant figures. For example, this 5679 kg, this number has 4 significant figures, right. Then second rule is all zeros occurring between non-zero digits are significant figures. Okay. What does it mean? So, take an example, this 2008, it is a number. So, now 2 is significant figure, 8 is significant figure, okay. Not figure, this, yeah. So, digit I can tell. So, yeah, basically non-zero digits, and between these non-zero digits whatever the zeros are there. So, that is taken as a significant figures. So, here number of significant figure is 4. Okay. Then third rule is all zeros to the right of the last non-zero digits are not significant figure. Okay. So far we have not considered the decimal point. So, it is whatever these 3 rules I am discussing. So, that is basically before decimal points, okay, or if there is no decimal points. So, all zeros to the right of the non-zero digit are not significant figure. Example 5960. So, this is the 0 at the right of this non-zero digit. Okay. So, this is not taken as a significant figure. Okay. So, in this case, although 4 digits are there, but significant figure, we are telling this is the 3 significant figure. Okay. So, there is a ambiguity in this rule. If you feel according to rule it is there, but it is difficult to digest it, accept it. Okay. In practical case, if you think that this 0 is significant, you cannot ignore it. Okay. So, then to consider it as a significant figure, so you have to write this one in different way. Okay. That I will tell you. So, we do not want to violate, because these rules may be useful, okay, in most of the cases, but in some cases it looks ambiguity. Okay. So, if we use these rules, then it does not represent our practical result. Okay. So, because in our practical result, if we fill this 4th digit here 0, this is significant figure, it should be significant figure, then this result you have to write in different way, that I will tell you, okay, using the decimal point. So, just violating the rules, we can just apply tricks and make this digit significant. So, 4th rule is in a digit less than 1, in a digit less than 1 means decimal point, there is a decimal, there will be decimal point, all zeros to the right of the decimal point and to the left of a non-zero digit, are not significant. Okay. So, what it is telling? If we take example the 0.00526. So, here it is telling this to the left of a non-zero digit are not significant. To the left of a, if it is less than 1, so it is a decimal point is there. So, it is this number less than 1. In this case, all zeros to the left of a non-zero digit is not significant. Okay. So, here then significant only 5 to 6. So, it has only 3 significant figures, okay, according to rule, and all zeros to the right of the decimal point, all zeros to the right of the decimal point, okay, to the right of the decimal point and to the left of the non-zero digit. Okay. So, this decimal point and this 5 to 6, so non-zero digits. So, between this 0 0 is there. So, that will not be counted as a significant figure. So, here effectively the significant figure is basically 3. Okay. So, 5th rule is all zeros to the right of a non-zero digit in the decimal part, okay, in the decimal part is or are significant, means 3.1790. So, this 0 it is to the right of a non-zero digit in the decimal part. Okay. So, this 0 will be taken as a significant digit, and then in this case this total this significant figure has 5 significant figures, significant digits, okay, significant, that is significant figures we are telling. So, this is the rule for writing the significant figure. Okay. So, this is very useful for writing the x based, Okay. So, as I told this, if x best, if 5960 as per this rule, this significant figure is 3, 1, 2, 3. So, this 0 to the right of this non-zero digit are not significant, but if you feel that this is significant, we cannot neglect this one, then basically we generally write just this way. We use one decimal point, but after that we do not put 0, where then it will have. So, then significant digit will be 5. Okay. So, just we put this, or you can write this x best equal to using 5.960 into 10 to the power 3. Okay. If you write this way, then what is the significant number here is as per rule you see this non-zero 596, this 3 is there, and this after in decimal part this 0 is significant now. Okay. So, then this your number significant number is 4. Okay. So, that is why just instead of writing 5960, then significant is basically this up to 3 digit. Okay. This number is 3, and then a significant figure is 3. So, but you take this fourth digit as a significant. So, then you have to write either this way or this way. So, these rules for significant figures, whatever these 5 rules I listed, okay, so that will not be violated. So, this what I am telling here basically how to write your result, okay, and that also is related with the your this delta x, okay, whatever the error. So, that will control your x best, okay, the significant number, what will be the significant number in x best, that will be controlled by the delta x, or it is related with also the delta x. And then this when you are okay fine, you have written significant, you have written your result considering the significant figure as well as taking care of the error delta x. Now, your result is you have expressed x equal to x best plus minus delta x, okay, and you have written say 596 say into 10 to the power 3. Okay. So, then plus minus you have to delta x you have to write. Okay. So, now there are different situation occurs when you do experiment and find out the result, and as I told you have to get confidence on your result, and for that we always compare with the we analyze our result, okay, we check our result. Okay. So, very frequently as I told this, there may not be standard result or true value with which you will compare. So, in that case we have to compare some other experimental result or theoretical result, or we have to repeat the measurement, okay, or you have to compare your result with the your colleagues or your friend's result, whatever he measured and got the for same experiment for same parameters what result he got. Now, then you have to see the discrepancy or difference. So, to get confidence on our result, so we analyze our result comparing with others. So, how to do that. So, that is what I am discussing. So, this we check the discrepancy or difference between two measured value okay, of the same quantity As for example, say you have measured the resistance and reported the result or got the result, say 15 plus minus 1 ohm. So, you know how to write the final result, because this 15 your error is there is no up to decimal point. So, it is a 1 ohm. So, you can keep only this you cannot keep your this 15.0 or something, right. So, you have to write 15 without using any decimal point. So, this is the result fine. So, after getting this result, now you want to get confidence whether your result is correct or not. So, how you can check it? You can check that if from lab someone, so this if standard value is given to you, so this is the standard value of this resistor. So, then you can compare with that. So, for that standard value, it is say telling this 16 ohm, true value is 16 ohm. Somebody is the company has given this value for this resistor. Then you can tell your result is discrepancy or difference between these two is 16 minus 15 is the 1. So, and then it is within the range of your error. So, you are reporting your result, basically it is you are telling this resistance of this resistor will be between 14 to 16 ohm. So, it is true value is 16 ohm. So, it is your result is very good, your measurement is quite accurate. So, this accepted value or true value, it is within your reported range, measurement range. Or it may happen the standard value, true value is not there, then your friends have measured this resistors of the same resistor and he got this value say 25 ohm, I think error reported say 2 ohm. 2 ohm. So, that means difference. So, then you have to see the difference is 10 ohm, 25 minus 15 is 10 ohm. So, an error range in your case 1 ohm plus minus, at this case is 2 ohm. So, this 10 ohm, this discrepancy is too high, it is not within the error range, it is not covered by this error range. So, definitely there is a mistake in the measurement. Now, mistake in the measurement of yours one or your friend's one, that one has to find out. So, so that means you cannot be sure about your results. In this case, it is controversy. Now, one of the both can be wrong, measurement of both one can be wrong, or your one can be wrong, this other one can be correct, or vice versa. So, in this case, so when this type of controversy result you will get, so then you have to repeat the experiment and check it. So, this situation may occur. So, I think I will continue discussion in next class. So, thank you for your attention.